Hi, Richard Walding here. I want to have a look at the topic in physics called the Standard Model. I'm going to keep referring to parts of the textbook. Now this is the Oxford textbook, and I'm going to have a look at, this is Unit 3 and 4, so I'm going to have a look at Chapter 13.1. Now I'm going to divide it up into two parts. I'm going to call this Part A. So in Part A I'm going to have a look at the Standard Model, and I'm going to have a look at really mostly about quarks, and then in 13.1b I'll have a look at leptons. Okay, now you don't have to know for the external exam the definition of the Standard Model. There's no requirement to know the definition, but I'll give you the definition because you'll need to, it'll be used in a lot of questions and you should know what it means. Standard Model is just a way of describing the three of the four fundamental forces that we know in nature, and also classifying the elementary particles. So I'm going to do that. Firstly, let's have a look. Let's say we've got all matter. Now you can divide up all matter in a number of ways. So in chemistry you might have done that into atoms and molecules, or elements and compounds, or something like that. What we're going to do in physics in this this section is divide that up into its elementary particles. Now, so I'll put a little arrow here. I'm going to put elementary particles. I'm abbreviating this, but you get the idea. So now an elementary particle is a particle that has no substructure. In other words, it's not composed of other things. Now you have to recall that. Okay, now that could be on the external exam as a multi-choice question, you know, which of the following defines an elementary particle, or you could be asked to define it yourself. It's more likely to be a multi-choice question and then give you some examples. You have to choose the right definition. So it's a particle with no substructure. That's it. Okay, now the elementary particles can be of two types. Ones that look after the forces, and ones that look after just your ordinary matter. Okay, so we're going to have a look at forces later on, but these things are called the bosons, and that'll make up 13.2 in the textbook and this little unit, or this video that I'm making now. But what I want to have a look at is the matter elementary particles. Now there's two types. There's quarks and there's leptons. Okay, now these bosons are broken down into a range of different ones, and I'll talk about that later. But as far as elementary particles for matter go, there are two, quarks and leptons. Now I'm going to do quarks in this section. Leptons will be in Part B a little bit later on. Now you'll notice there's a box here without a word in it. Now there is a corresponding word to bosons. Now boson was named after a Indian physicist, Satyendra Bose. Well, he actually did most of his work in Calcutta, but he did a lot more work later in life in Dhaka in Bangladesh. And I've been to his laboratory, quite fascinating. But that's Bose, and his bosons are named after him. And this one here is fermion. Now that was named after a Italian scientist, Enrico Fermi. He went to the US. But you don't have to know that, right? So that word is not in the syllabus. You won't see it anywhere. You won't see it on the exam paper, I'm pretty sure. Even as a red herring, I doubt if they'll use that, because it might get too confusing. And I don't think the writers of the exams would be that mean. You will see bosons, and I'm going to divide that up a little bit later. So I want to have a look at quarks and leptons. Later on I'll also have a look at the antiparticles. Now you have to be able to define an antiparticle as well as a particle. I'll mention now the definition in the syllabus is a little bit weird, because not a lot of people agree with it, but you have to learn it because it's in the syllabus. And I've put it in the textbook as they've got it, but I've explained that it's a bit tricky. Basically, an antiparticle is the same as the particle, except that it has the opposite charge. So if you had a particle, say an electron with a charge of negative, one negative, an antiparticle would be one positive. Now the syllabus also says and or spin. Okay, now spin is a particular quantum mechanical thing dealing with, it's a magnetic property of the particles. You don't have to know anything about spin. Spin is not mentioned except in that definition of antiparticle. Now they don't have to have opposite spin. They can have two types of spin, but they don't have to be opposite to the particle that they're associated with. But I've said to my students, just write it down as the syllabus has it. If it's multi-choice, you know which one to tick, even though, you know, if you talk to physicists, they'll say, this is a bit weird, I don't think it's right. And I've checked that out many times with physicists, so, but just leave it in. I think they got a bit tangled up in there somewhere. Okay, what I want to do now is have a look at quarks. Now the pronunciation of that, I say quarks. The guy who originally coined the word was tossing up between quarks and quirks, or quarks. A lot of people, a lot of physicists will call it quark, to rhyme with talk, and others will call it quark, because the original poem that it came from was talking about a person called Mark, Mr. Mark, M-A-R-K. So, you know, even the person who coined it, Murray Gell-Mann, his name was, he said, you know, quarks, quarks, it doesn't really matter. So I'll call it quarks, but it's up to you. Okay, I'm going to rub this off so I can make room for quarks, and then we'll talk about these quarks. Okay, let's get rid of some of this. And now, what you have to know are the 6 types of quarks. Now the syllabus says list or name, no, sorry, recall, I think they say, recall the 6 quarks. That's it. You don't have to do any more, you don't have to know any other properties or anything like that, just recall them. Now you could teach that to someone in grade 4. So there's got to be more to the physics syllabus than that, or the physics course than that. And you'll see later on, even though you mightn't learn the names off easily, you need to be able to do a few things with them a little bit later on. Now, there are 6 types of quarks. Now I'll just write these down. They're up, down, charm, strange, and top and bottom. Now, they're the names, and they have the symbol like this: up, down, charm, strange, top and bottom. Now, they're all lowercase letters for that. Now, on the exam, if they say to you, recall, list the 6 quarks from the Standard Model, or just list the 6 quarks, you can do 2 things. You could just list those 6 names, right, and you'd get your mark. That'd be it. Or you could list the 6 symbols. Physicists know them by their symbols more so than their name, so you could list those and you get your mark as well. Now if you think, oh, I'll show exactly what I know, I'm going to put down both, that's fine. But if you mess one of them up, say for instance you've got the symbols back to front and you put B and T because you're in a rush, you lose your mark. So I don't know what's the best thing to do. I would just list the words and you're safe, or list the symbols and you're safe. I mean, I'd do that in case the examiners changed their mind. Last year, when I was marking, they said we said either of those 2 is okay. Now, you'll notice we can break these up into, whoops, that's not right. We can break them up into pairs like this. Put a line through there, and we call that 1, 2 and 3. Now that's called the generation, G-E-N. So this is the first generation, second generation and third generation. And that's roughly in the order they were discovered. So these were first discovered, and they can constitute probably 90 something percent of the universe. Probably about 98% of the universe is made up of up and down quarks. These things are very unstable. Look, some of these quarks are quite heavy and very unstable. So the ones you are going to deal with mostly are the up and down quarks. Okay, now look, I'm going to tell you this. This is the electric charge. So the charge on each one. Now there is a pattern to this. Now the first member of each generation is plus 2/3 E. Now that E just means elementary charge, like the charge on an electron is -1 E. So the charge on an up quark is 2/3 E. The charge on a down quark is minus 1/3 E. This one here, plus 2/3 E, minus 1/3 E, plus 2/3 and minus 1/3. Okay, it's not hard to remember, and I tell my students just learn it because it comes up. It's useful for things a little bit later. Now I'll come back to that when I'm working out the charges on things like protons and neutrons and mesons and so on. Okay, so learn that. That's all you have to learn. Learn what the Standard Model is and learn that definition I told you about elementary particles being no substructure. Okay, now the other thing is each particle, each quark has an anti-quark. So there's an antiparticle. I'll put it here. Antiparticle. Now remember I said it's the opposite charge. So it has the same properties but opposite charge. And the syllabus says and or spin. So you can write that down if you like. And it doesn't really matter. I personally don't think they'd give you a question which had that stuff about spin in it, because there's a bit of a debate about it, and I'm not so sure that they'd want to get involved in that. Now, the anti-up. Look, I'll put this. I'll put the words here first so you can see them. So this will be anti-up, and it has the symbol U with a little bar on the top. The little bar above it means it's the antiparticle, and this will be an anti-down, and that's that. And of course we've got anti-charm, anti-strange, anti-top, anti-bottom. Now I won't write the words in, but you'd have anti in front of each one of those. Now the other thing is the charge. Look, the electric charge will be -2/3 and plus 1/3 and so on. -2/3 plus 1/3. Now you don't have to, like I said, you don't have to know the electric charge, but it helps when you're working things out. Now certainly if you're doing an assignment on this, your research investigation, you might go into the meanings of a lot of this and how they bond and how you get composite particles and the origins of the elements, you know, through Big Bang and so on like that. Okay, now I can basically leave that there. I've discussed the names of the particles and their symbols and the antiparticles and their symbols, and saying they have the opposite charge. Okay, that's about all there is to that section. What I'd like to now do is to look at composites of these, okay, because you don't get these quarks existing by themselves. They don't exist by themselves, they exist in groups. Okay, and if you try and pull them apart, say you had an up and down quark near each other, you pull them apart, what happens is the energy that you put into it goes to creating another virtual pair of opposite particle and antiparticle. So you pull them apart and two more pop into existence. So you end up with the same sort of thing. You're not achieving anything. Okay, let me get rid of this and I'll talk about composites, but I'll refer to these numbers, but you'll remember that. Okay, now we've got, these are quark composites, so I'll put it here because I'm only talking about quarks at the moment. Now anything with anything with quarks in it is called a hadron. Okay, now this is a bit tricky. The syllabus doesn't ask you to define a hadron. You don't have to recall it or anything like that, but they'll use that in the exam as a red herring to try and trap you. Okay, so it's a useful term, and it's a shame it's not in the syllabus in some ways, because we can refer to it. And the same for that fermion I told you about. It'd be nice to be able to refer to that as well. But let's have a look at these quark composites. Now, a hadron is a composite. Now, composite means not just one quark, but it could be 2, 3, 4, 5 quarks or whatever, but more than one quark basically. You've got two types of composites. One is a baryon and two is a meson. Okay, now what you have to be able to do, so the two types of hadrons, in other words two types of quark containing composites, are baryons and mesons. Now the Greek word barys, B-A-R-Y-S, means heavy. You might have heard of a barotrauma, in other words, or bariatric surgery is a good one, where someone who is trying to lose weight has bariatric surgery to reduce their weight. So I'll deal with baryons first. Now, a baryon is made up of 3 quarks. Okay, so it's a composite of 3 quarks. Now, I'll just get rid of the meson part because I need a bit of room. Now, the syllabus distinctly says a baryon is 3 quarks, and that's what I've put in the textbook. I've stuck to the syllabus, and I've stuck to the common use of the word baryon, which is 3 quarks. Now, some people will say a baryon is any composite of odd numbered quarks basically greater than 1. So 3, 5, 7 and so on. A composite containing 5 quarks was discovered a couple of years ago, a pentaquark, but according to the syllabus and according to my text and according to most physicists, a baryon is 3 quarks, and we just leave it at that. I think in Victoria for the VCE they allow 5 quarks. Any odd numbered composite of quarks is a baryon, but we're sticking to 3 quarks. That's what the syllabus says, and we don't want to sort of get tangled up in a dispute about the right alternative explanations of baryons. So 3 quarks. An anti-baryon would be just this. It would be 3 antiquarks. Okay, simple as that. So let's have a look at some baryons. Now, I told you before the simplest one are the up and down quarks, so let's stick with these. Now, if you had up and down quarks, that's a proton. Now, if you wanted to check that, what you'd do is look at the charges on the 3 quarks and see what it adds up to. Now, an up is 2/3, another up is 2/3, and the down is -1/3, and that gives you +1 elementary charges, which is what you would normally know as a proton. Now, if I were you, I'd learn that. Okay, so what you have to learn for this section is the word quark composite, what it means more than 1 quark, a particle, a subatomic particle consisting of more than 1 quark. Now, I use the word subatomic. It's normal to refer to all of the work we're doing as subatomic, because you think there's the atom. You're talking about the nucleus mainly, which is it's within the atom. So you have to know what quark composites are, the 2 types, and be able to define each type. So I'm defining the baryon as 3 quarks, or antibaryon as 3 antiquarks. But you should learn the quark composition of the baryon called a proton as up, down. Now, you'll need that later in a chapter 14 when we talk about particle interactions. You have to be able to show the quark composition of a proton. Now if you look at the other one, up, 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 down, down, this is a neutron, and again you should learn that off by heart. Okay, now this would be plus 2/3 minus a third equals 0. Okay, so it's as simple as that. Now so that's defining those two. Now there are other combinations. You could have an up, down, strange for instance, that's one they have found, and that's a lambda, L-A-M-B-D-A, that sort of symbol like that. Okay, now normally you call a proton as just a P or a P plus, and a neutron is N, just to get that clear. Okay, now that's the main part about baryons. That's really all you have to know. You have to define a baryon. We've done that. Let's move on and define the meson, the other one I told you about. So we'll get rid of this, and I should have said, if you had an up, like up, up, down is a proton. If you had this, anti-up, anti-up, anti-down, this would be an anti-proton. Now if you wanted to check, it should have the opposite charge to that. So an anti-up will have opposite charge. So an up was 2/3, a plus 2/3. This is an anti-up, so it's minus 2/3, minus 2/3 for the second anti-up, and plus a third, which is the opposite of a down. So an anti-down is plus a third. And if you add all that up, it comes to 0. Now that doesn't look right. Yes, it does. No, sorry. That comes to minus 1. 4/3 plus, yeah, minus 1. Okay, so we've done the types of baryons, the baryon itself and the antibaryon. Let's now move on to meson to finish this off, and it's like this. Meson is, it's a word, it's a Latin word that means middle, so it's a middle mass. They used to think, you know, between an electron and maybe the protons, there's things of middle mass, and so they call them mesons. It's like the word median. You talk about median strips in the middle of a road, or the median value of a house or something, and in maths you would have learnt median, mode and mean. So median is middle value. Okay, a meson is defined as a composite particle made up of a quark and an anti-quark. Okay, now the question is, can you have an anti-meson? Well, you could, but you'd still end up with an anti-quark and a quark. So you can have anti-mesons, but in general it looks like you can't. But let me give you an example of some. Now, a simple one is the pion, an early one discovered. Now you will have met that in your special relativity chapter when you talked about the muon experiment, where they were trying to confirm the idea of relativity, Einstein's special theory of special relativity. And we talked about pions being created in the upper atmosphere, and they decay into muons, and the muons then decay. But these pions have the symbol pi. Now they can be plus, minus or 0 depending on what they're made up of. So for instance, if you had an up and an anti-down, let's start with an up and an anti-up. Make it even simpler. Okay, now the electric charge on that would be plus 2/3, and now an up is plus 2/3. This is the anti, so it's minus 2/3, and it's 0. So no charge. If you had an up and an anti-down, it'd be plus 2/3 minus, plus a third, because a down is minus a third, and this is the anti-down, so it's plus a third, and that would be plus 1. And we could also have, say, a down and a anti-down, so that'd be minus a third and plus a third, and that's 0. And we could have a down and an anti-up, for instance. So it'll be minus a third plus. Now an up is normally plus 2/3, so it'll be minus 2/3, and that would be negative 1. So the pions could be 0, 1 or negative 1, and they're often shown as, where will I put it here, pi 0, pi plus, and that'll be a pi 0, pi plus, pi minus. Okay, so a negative pion, neutral pion, and positive pions. Okay, now if I said to you, what's the antiparticle of this? Okay, all it would be is the D would be anti-D, and the up would be the anti-up, which would be up, so it would look like that thing there. So that's this thing. Okay, so the antiparticle is that one there. Okay, so mesons can be charged, and that's important for later on, because you'll notice not all mesons are charged. Some are 0 and some are electrically charged. Now when we do forces, the fundamental forces, one of the fundamental forces is the electromagnetic force, and it only acts on particles that are charged. So not all the mesons will be affected by this electromagnetic force, only the charged ones, and we can leave it there. Okay, that's basically all there is to that first section, so I'm going to stop there and we'll move on to 13.1b, where we'll look at the leptons in a minute. Thank you.